Okay, hello everyone. In this video, I would like to introduce our hackathon prototype sensor node. As we know, we are currently in developing of AI inference sensor nodes to detect the forest fire in Indonesia. Okay, as you can see here, this is our first prototype of sensor nodes, AI sensor node, or we call it IoT edge sensor node. In the box, you can see here in my right hands. First is the box. And then here is the solar panel. The output of the solar panel is 5 volts, and yeah, it's look chaotic, but here is the camera. I should open the cap first. This camera is attached to makes bit our IoT edge hardware, and this one is our temperature measurement, temperature and humidity measurement. We are using DHT22 sensor. This one is MQ9 sensor to detect gas. Okay, we might want to take a look more inside of the box. Okay, we need to open the box first. Let me set up the place. Okay. Okay, here it is, our hardware. Okay, it's looking good. Open our hardware. Actually, solar panel is connected to solar charger controller called MQTT solar charger to perform charging and discharging to our hardware. So here it is, our hardware right now. Okay, before we go through the hardware explanations, okay, it's good. Okay, you can see here, this is our AI device that is Mike's bit that attached with the camera, and here is our solar charger controller here, MPPT solar charger controller, and we need, buck boost converter for 5 volt. This hardware system is supplied by 5 volts, but as we know, the battery only capable to deliver like 3.7 volt, so we have to give it the boost converter here to 5 volts. And here it is, our Wi-Fi device to sending our data to the cloud. Okay, let's take a look at the back of the board. Carefully moving the board. We have to detach the solar panel first. Okay, good. And you can see here is the battery. consists of two 865 battery capable to deliver about 10,000 milliamp hours. Okay, for detailed explanation, let me share some information for you. Okay, maybe we want to go back to our previous proposal of the hardware design. All right, here is our proposed hardware design for the IoT sensor node. Actually, as we've seen earlier, that the hardware consists of several devices. Those are the Wi-Fi module. This is the top view of the board. Consists of a Wi-Fi module and 4G modem. These are the alternative connections for sensor nodes. Of course, we touched another two sensors. Those are gas sensor and temperature and humidity sensor. We have power supply diagram, our IoT edge device, and also the microstrip antenna. And here at the back, at the bottom view of the board, as we seen in the previous, you can see that the board was attached with two. Actually, we prepare for 3 batteries, but in the previous shown that it's only 2 battery. And here is the main diagram of our hardware. The solar panel will, will power the battery first, while charging and discharging. The solar panel will charging the battery when daylight, and the system will be powered by the battery here. Okay. From the system, this general diagram, we want to realize the idea of the hardware system by designing the PCB. So we come to the PCB design. Let me open the application first. Okay, now I will share. Wait a minute. Okay, I will share the screen. Okay, this is the PCB. PCB we design node, PCB node using KiCad. Let me open the project called Hackathon PCB. Here we try to realize the idea into the things. Let me explain. Actually, there's several blocks. Call it ASP minimum system. As you can see later, the device, and then this is the modem design as alternative, and this is the sensor. Just of gas data, temperature measurement data, and battery status. And here is the pin header connected to our IoT edge. Actually, the system is controlled by our IoT edge. device makes bit. They can control the ESP's minimum system by triggering the ESP enable pins. So it will open what is called, let me take a look here, VCC enable. It will open the gate here to let the current flow through the ESP device here. And here is some standard circuit to what is called like to download the firmware using through these pins. And this is the minimum system that we have to design the board. Okay, then we go to the top and let's see the modem PCB design. Yeah, standard PCB design for the modem, and for the sensor provide put the purpose module here, the sensor, solar charger. Okay, and battery holder here also here, and this is the switch on off to perform on and off of the main power. I also put some protections at the output of the boost converter. And let's see the PCB that we designed. Here is the prototype PCB. Let me. Okay, this is the minimum system of ESP32, and this is the this is the circuit of our modem, and this is the connector to the makes bit, and this is connector to the our sensor, and this is the boost converter module. Yeah, since we are in limited time, we have to provide as soon as possible, so we choose a fixed model. And here we also using MQTT model solar charger. And take a look to the 3D boards. As we can see here, it's clear to see. It's good to see that everything is in order. Our modem, or SIM card here, our battery holder is exactly the same like what we've seen before. Boost converter, the Wi-Fi nodes, the modem, and the MQTT solar charger. And then we might want to see like what's inside this hardware actually. What's that's running this board. So we provide the GitHub links for you to see. Let me open the GitHub link. Oops. Here is our GitHub Hackathon. See, as we can see here, several folder and files consist of several informations like first is backup model. Actually, we try like 2 model from our training. Okay, let me explain about our IoT edge device a little bit called makes bit. Here's the pinout of our makes bit. As you can see here, actually they have this little processor called like Kindred processing, Kindred K210. They claim that they have a Kindred processor that can run the convolutional calculations. It costs not that high, about $30. Capable to run the inferencing for IoT edge. So this is our IoT edge that we are going to use. And here in this folder is the dataset that we collect from the several source. Actually, we have Fire2, and Fire folders, and we combine the three of these folders into mixing folders, consists of like 2,700 image inside the folder, and also XML file. These XML files inside of this XML file is what is called like labeling. Yes, the image labeling for our training. Yes, as we mentioned earlier, that we want to provide supervised machine learnings or supervised deep learning. So we have to labeling our image. Is the example. Yeah, if you want to know how we labeling our image, we use label EMG. Let me. My God, where's the file? Let me search it. Here it is. Label EMG.exe. So we can see here, we can open the folder if you want to open like Hackathon, Codegreen, dataset, mixing, image, it's like folder. This is our change XML. Good. So we click. Sorry. Setters and dataset. XML. Open. There you go. We got to label this one. Image, the fire. Where is the fire? And yes, forgot to mention that we have two classes to detect. These are smoke and fire. But to labeling everything in this image is quite a lot of works and efforts, of course. Here's the smoke, here's the fire, fire. Okay, let's slide info for labeling. Okay, let's back to our GitHub. Then we go to ESP firmware folder. Yes, this is the ESP Wi-Fi device that we want to use. The board ESP firmware, you can see. Actually, you want to know what is the functions of ESP here, I will explain. I will explain in briefly that the data from IoT Edge makes bit the inferencing results or the probability results of detections from the fire and smoke will be sent through UART and will be accepted by the ESP. The ESP will pass the data through using Wi-Fi to our MQTT broker. So the communications using, yes, our sensor not using MQTT communications protocol to our MQTT broker. We will show the result later of this hardware in the next video maybe. So let's explain a bit. In the SP firmware, there are main folder consists of the main code. Okay, let's open the main code. Here, let me explain a bit about the code. Yeah, actually I generate a hello world example first. We need only the library here, like free RTOS, the ESP system, and our custom library or module like MQTT, Wi-Fi, UART, and dish T22. Here is our SSID name. Well, actually, it's not. So here, let me explain about the firmware will run this code only, the main code. First is they need to initialize the hardware, and then it will run our routine function or routine thread called the routine task with the routine functions. That's all. It's only running the routines here. And for the function initialize, first is you need to initialize the Wi-Fi. Like we need to setting the SSID, password of SSID, Wi-Fi authentications, and then things. The SSID should be changed with change. Okay. And the UART init. This is the communications, your communication that we have to initialize to be able to communicate to our max bit hardware. And this is our MQTT broker address. Actually, I developed the broker inside Raspberry Pi, and the topic is sensor data, and here this the ADC data that we use. Actually, there is change design. I realized later that actually our max bits IoT Edge hardware have no analog to digital converter. So Since the ESP32 have the ADC, so the sensor will be read directly by ESP32. And here is our routine functions. It's yeah, actually the routine function will read the data status if our makes bit or our IoT edge sending the data through the UART. Sorry. It will
Oh God.
okay. Test. Okay. If
Test. Okay. Okay. Sorry, my microphone was off. So let's continue to explain the firmware of our ESP Wi-Fi device. So after we initialize the URL, the MQTT address, topic, and the ADC, we go to the routine task. The routine task actually consists of the task data state. When there is incoming data from our IoT edge, makes bits, the state of the data will active and trigger this flow program, and it will publish the data to to our broker, the MQTT broker. This is how to read the sensor data. We have to read the ADC and read the HD data and convert them into temperature and humidity, gas data, and battery data. Okay, go back to the main GitHub. And this is the Hackathon PCB that I explained before. You can open it in KiCad software. Yes, actually, the process of manufacturing of the PCB needs about 3 days works. For this one, we request or we purchase the PCB productions in China, and for the design PCB itself needed about 3 days, and for the manufacturing needs about 3 days, and the transportations, needs about 1 week to transport the PCB to our home. So it needs about 2 weeks progress. Okay, then we move to test codes. What's inside? Actually, it is the test code that we test into our IoT Edge device. Consists of Python programs. For example, this is the main program that we deploy in the MaxBit. This is the test image 2, and test UART. Okay, then what's inside the make string? Actually, the makes bit provides example how to create their model, their AI model, and run in their device. Actually, they have installed in their library like TensorFlow. Sorry, I mean like AI algorithm like YOLO and MobileNet. Here is the example how to run the code. Here we need only to prepare the data set. Here copy the data set here, and here we train using YOLO algorithm to detect the fire and smoke. Actually, it is the open source, so we need no license for this one. The output of training is actually the TensorFlow Lights model, but using, let me explain a bit, using what they call incense, sorry, or NCC tools. The NCC tools, this one will convert the TensorFlow Lite model to Kindred's model, we call it, with extension file K model here. Results K model. So here's the report. Actually, it's good enough. We got the train using about 30 epoch with the maximum of 40 epoch, and got small loss. Okay, let's take a look. Here is some images of our sensor nodes in the GitHub. And okay, after we got our model, after we trained our model using YOLO, and we got the output of the models, we convert into the Kindred models, and then we have to run the main. Here is the sorry, is the main code. Let me explain briefly. We have to like import several library provided by MaxBit firmware, and like we have to announce the UART, and we have functions, send data functions, and here is how to run our model. Like we have to define like sensor window. It's using like 224 pixels times 224 pixels. Here how we actually this meant programs not deployed to detect the actual image, but we only test it using forest fire image, for example, image fire 5. But if we want to take the real image, I mean take the real time or real situation image, you have to perform image snapshots from the sensor, from the camera. But here I test our accuracy of our AI using testing image. And here is how to perform the bounding box. Like we draw a rectangle and related to the positions, we draw the string consists of the labels and the value of the labels. We also later the results of smoke and fire detections. If you want to send the data on the value of fire detections, just simply save the value into temporary value, and send the data through UART. Okay, let's go back. Actually, I want to show the results of our image of fire detections. Okay, this is the sample of our results. Actually, the detection of fire and the smoke from several images to test the AI. The model is good enough. Actually, I think it's performed good detections. Yeah, I think from this picture. Actually, I record this from my phone and showing the detections of fire and smoke through the LCD from MaxBit from the MaxBit kit. Here we can see the detections to the image. Okay, the result of the training model and AI inference from the IoT edge MaxBit. Where's the buzz button? Okay, let's continue. Okay, this I have shown the detection results from the previous video. So the results, as I mentioned earlier, the result of detections or the probability of fire detections will be sent to the cloud using Wi-Fi and MQTT protocol to our broker. Unfortunately, we cannot provide the perform right now because of the time limit. We cannot provide the platform, so we just can show the data to our MQTT broker. So let's get started. Here the example, the result. Actually, this is the MQTT broker that I deploy on Raspberry Pi to receive the data from the sensor. As I mentioned earlier, the data the MaxBit or AI IoT edge hardware will send the fire detection and smoke detections probability and that sensor will be measured by the ADC, not the digital converter from ESP. So let's get started. Okay, we are using Mosquito clients. Mosquito subscribe to localhost, meaning that I subscribe to internal broker of MQTT server with the port of 1883 and the topic is sensor data. Okay, this MQTT. The service will listen to the data that come from sensor. So we will not just turn on video. We just need to turn on the power. It's the power button, on off button, whatever. Good, everything's good. So wait till the Wi-Fi connected, the MQTT connected. There we got fire detection from the image fire 5 is 0.8, about 0.8. The gas voltage is the integer value. Actually we need to convert it later to the original value. Also the battery value is integer value. Temperature is to 0. There we got the output of temperature, humidity 27 degree. It's a good temperature. I think it's actually content. Actually in Cimahi or in Bandung is about 27.8 at Celsius, and the humidity is 70. We got heavy rain actually at the afternoon yesterday evening. Here, since we are not changing the image, result will be still the same. Okay, that's all of the demonstrations of our video. Hope it will explain everything that we want to know about our sensor node here. Right. If there's time, I can provide a platform to show our data, or even better, to show our image captured by this sensor node from Resyst radio and embedded system technology. Thank you very much for your attention. I would like to say please subscribe to our video, and probably this next some particular interesting video provided by Resyst. Thank you very much. Goodbye. Where's the button?